Okay, hi, I'm Isha. I'm a first year PhD student at the ULB, and today I'm going to be talking about the Radar Echo Telescope, or more specifically, the work we've been doing in exploring properties of radar signals from cosmic rays and neutrinos. And the picture in the background here is of the RET-CR experiment, or the Radar Echo Telescope for cosmic rays. And this is important both for this work and for RET in general, so I'm going to come back to it in a second. But first, I want to talk about the overall aims of the RET collaboration. So what RET is aiming to do is to detect ultra-high energy cosmic neutrinos with in-ice radar. And this will be the task of the RETN neutrino telescope. So to put this in some context, on the left here, we have a slightly familiar plot. So there's a mixture of upper limits and sensitivities for future and in-progress experiments. But the bit to focus on is this dashed red line here. So this is the projected sensitivity for a preliminary RETN detector setup. So what we're aiming to do is to fill the gap between PeV and EeV energies. So from the end of the current range of detections, or most of the current range, up to EeV energies, at which point different detectors, such as RNOG and a lot of the other ones up here, have good projected sensitivity. And RETN is also a scalable concept, which means that it's possible to act as a complementary detection mechanism at higher energies, which gives us an increased range of physics observables, which is always good. But how are we using radar for this? So when a ultra-high energy neutrino interacts in ice, it produces a cascade of relativistic particles over here. And as that cascade propagates, it leaves behind a trail of ionized charges. And this trail is actually capable of reflecting incident radio signals. So if you illuminate your volume with a transmitter, these radio signals hit the ionization trail and are reflected, and then you pick up these reflections in the radio receiver, and this forms your radar echo signal. So this is the basis of the radar echo method, the feasibility of which has been demonstrated at the STAC accelerator in 2020 by the newly formed RET collaboration. And you can see the experimental setup on the right there. But in order to get from this setup in the lab environment, to a large-scale neutrino telescope, RET took the intermediary step of RET-CR. So RET-CR is a pathfinder for RETN, where instead of looking at neutrinos, we look at cosmic ray air showers. Over there. So this is for a number of reasons. So when a cosmic ray air shower of a high enough energy impacts a high altitude ice sheet, it actually deposits a fraction of its energy into the ice sheet, and this forms a secondary cascade in the ice here. And this secondary cascade actually closely mimics the one by our target neutrinos, which means that we can use these cosmic ray air showers as a test beam for the radar method to show that we can detect these in-ice cascades. And cosmic ray air showers also occur more often, so we have reasonable event numbers, and they're also detectable above the surface with well-established techniques. So here we have radio antennas and scintillator panels, and we use the surface detections both as a trigger mechanism for the radar system and to validate the findings of the radar system. So RET-CR was deployed in 2023 for a short period, and in 2024 from May to August. And I have another picture here on the right from 2024. And deployment of this latest 2024 data is currently ongoing. But what I'm going to focus on now is exploring RET-CR signal properties. So what we've been doing is simulating radar signals in an RET-CR setup. And this is for a number of reasons. So one is to make sure that we fully understand the signals that we expect to see in RET-CR. And it also helps us gain a detailed understanding of the radar signal, which means that we can then use it to help develop reconstruction methods for the future neutrinos that properly make use of the radar signal. So in order to do this, I'm using the MARIS simulation code. So this is a semi-analytic code that uses parameterized cascades and simulates the expected radar signal from these cascades for a user-defined geometry. And I've got that on the left here. So we have a transmitter and a receiver, and I'm focusing on a single antenna pair that mirrors the dimensions of our RET-CR. And then we have our cascade in orange from the top there, and that always originates from the XY plane or the ice surface. And then there are a lot of free simulation parameters, and I've picked out a few at the top right there. For a single event in MARAS, you start at your transmitter, you produce radio signals with your transmit frequency, which in here is 250 megahertz. They propagate through the ice, and I'm using a constant ice density and refractive index, and then they hit your cascade. Some of that will reflect, and then that's picked up in the receiver. And that gives you this voltage signal here. So at the top is a normalized voltage waveform, and I'm always using normalized waveforms here. And at the bottom, I have the corresponding FFT. And I've picked out two variables. So there's the peak amplitude at the top, and then the peak frequency below. And I'm going to focus on these two variables throughout. And the idea then is to explore how these variables change for different cascade positions and arrival directions. So if we start with position, on the left here, I have a grid of simulated cascade positions. Each orange dot is an individual signal, and I picked out 3 example signals on the right there. Then for each of these signals, I take the peak amplitude and I plot that on the left plot respective to its position. So that gives you this view here. So that gives you a nice overview of peak amplitude with respect to the cascade position. And then we can do the same for arrival direction. So if we go back to this diagram here, I've now got a fixed position. In this case, it's 15 to 20 meters. There. And then I simulate a grid of different arrival directions where each dot is a different direction. And again, for each dot, I plot the peak amplitude, and that gives you this plot here. So just to make sure this is clear, at the center of the polar plot, you have cascades going horizontally downwards into the ice. As you move out along the radial axis, you move to steeper zenith angles. And as you move clockwise around the polar axis, you move to different azimuth angles. And here we see 3 distinct features. So you have this vertical high amplitude region, you have this fluctuating ring of amplitudes on the left, and then you have this striped effect of low amplitudes on the right. And I'm going to return to these features in a second, but the main thing to take away from this is that we see relatively significant fluctuations in the peak amplitude according to cascade direction. And what we want to check is whether this is just for this position or if it's a constant across the detector. So the way we can do this is by moving things around a little bit. This is the same plot as before, and I'm going to move it to the position that it originated from, so 15, 20 meters. And then we can simulate a whole range of different positions. And the white dot in the center of each plot is the direction that the cascades in the plot originated from, and the arrival directions are the same range as before. So we see that the bright amplitude regions from before are visible for all positions in this plot, and they're always curved towards the transmitter and receiver. And we actually found this to be a coherence effect, where for a particular arrival direction, the individual signal contributions that make up the final signal actually arrive at the receiver in phase with each other. So they sum coherently and they have boosted amplitudes, and that causes these bright regions. Okay, so then what about the other 2 features? They are also visible in here, but they're a bit harder to spot. And they're actually a lot easier to see and to understand if we move to the peak frequency instead. So here, I'm plotting the peak frequency on the color scale, and you can see a range of different frequency shifts according to the direction. And the bright regions from before always correspond to a strong frequency response at the transmit frequency, which I've indicated there. But we also see that the rings from before are now high frequency shifts. You can see there and there. And then the striped regions are low frequency regions. So well, actually, because if I start with the ring on the left here, we see that the individual signal contributions now arrive at the receiver pretty much simultaneously, which causes this strong frequency shift. And this can also be understood as the same effect that causes the Cherenkov ring, which means that it will always occur in the simulation at an angle defined by the refractive index of the medium, or the Cherenkov angle. And then we actually see the reflection of this effect in these red stripe regions here. And this is because of the bistatic setup, where we have both a receiver and a transmitter. So these striped regions will always occur at the supplementary Cherenkov angle, and they will always be focused towards the transmitter instead of the receiver. And that brings me to my summary. And I'm going to leave it there because I'm over time. Thanks very much for listening.
Thank you, Isha. Are there any questions for Isha?
Thank you for the nice talk. So can you give us an idea what would be the angular resolution for like a full detector? Is it like degree scale or larger than that, or?
We are aiming for degree or sub-degree scale.
Sub-degree.
But it all depends a little bit on how well we can use these properties to actually, well, exploit them and then get to that scale. And that's all sort of studies that are being done in the future.
Yeah,
but that's the goal.
Are there any other questions? If not, let's thank Isha. Are there? Wait. Okay. Sorry.
So I mean, you talk as well about the RET as a cosmic ray experiment. Do you have?
Sorry, I didn't catch that.
You talk about RET as a cosmic ray experiment as well. Do you have any sort of idea of what's the sensitivity for cosmic rays, and why particularly neutrinos, and not also like target your experiment towards cosmic rays?
So the RET-CR is specifically targeted towards cosmic rays to essentially prove that our method can detect these cascades. So we don't have particularly competitive sensitivities because we're not really trying to do cosmic ray science. We're sort of trying to prove the method. And then RETN won't be aimed specifically towards cosmic rays. So they're sort of separate ideas.
Okay, thank you.
Are there any other questions? If not, let's thank Isha again.